Uh, Good morning. In the previous class, we have gone through the problems related to the leaf spring. Today, we go through the last concept under the leaf spring, that is the Bellivellie spring. Bellivellie spring. Let us see what is the meaning of the spring. Bellivellie spring sometimes we also call the disc springs. Here, disc springs also called the Bellivellian spring are used where high capacity compression springs must fit into small space. Means if the area is too small, then in that case you are going to use the Bellivellie spring. It also high capacity of compression. Here, high capacity of highlighted is a high capacity of compression spring. Bellivellie springs are nothing but these are high capacity compression spring going to use in a small spaces. Each spring consists of several annular discs, okay, that are dished to a conical shape as shown in the figure 3.22a. That figure I will show here. Here, this is a conical disc shape. This one conical disc shape figure, and there will be bounded like this one by one. Okay, they will mount one by one, and this will become a Bellivellie spring. This will become a Bellivellie spring. Clear? Next, so this is conical as shown. They are stacked upon one on top another as shown in the figure 3.22b. When the load is applied, the disc tend to flatten out, and this elastic deformation constitutes the spring action. What is the meaning of this one? What is spring here? When the load is applied, the disc tend to flatten out, and this elastic deformation constitutes the spring action. Okay. For example, Bellivellie spring in safety valve. I'll tell you what is the meaning of this one. Consider here. When the load is applied here, I'll draw this diagram. When the load is applied here, this spring is going to flatten, means it is going to extend. This extension of the spring is nothing but spring action. Clear? When the load is applied, this flat spring is going to extend. This extension is nothing but spring action. Clear? And now what is our aim here? Our aim is here to find these values, this dimension di, h, d naught and t. The design of Bellivellie spring indicates you have to find di, h, d naught, d. These are our dimensions. That is, what is the meaning of di? Di is the inner diameter. D naught is the outer diameter of the spring. H is the height of the thickness. Height of the spring. H is the height of the spring. D is the thickness. H height, di and d naught are inner and outer diameter. T is the thickness. Now let us see what are the related formulas here to find the stresses. Only three formulas are there: 20.19, 20.20 and 20.21. 20.19 is for deflection, to find a deflection of spring. 20.20 to find the inner stresses induced at the inner edge. 20.21 is to find the stresses at the outer edge. Deflection of the spring is given by Yf equal to 4Ey 1 minus Poisson's. This symbol indicates Poisson's ratio. M d naught square. I'll tell you what is the meaning of this M. H minus y divided by 2 into t cube, equation number 20.19. Here this M indicates a constant. This is a constant. I'll tell you what is the value of that afterwards. Next, the maximum stress induced at the inner edge. That is sigma I. Sigma indicates stress, I indicates inner. So it will be denoted by sigma I. The formula is 4Ey. E means Young's modulus, Y means deflection. 1 minus Poisson's ratio square, M d naught square, C1 H minus Y by 2 plus C2 H2, equation number 20.20. Here this M, C1 and C2 indicates the constants. These are the constants. Next, maximum stress induced at the outer edges. Sigma naught 4Ey 1 minus v square m d naught square c1 h minus y minus c into d2. The difference between inner edge and outer edge equation is presented here. Only plus and minus symbol. If plus is there, sigma I. If the minus is there, sigma naught. If the plus is there, sigma I. Minus is there, sigma naught. Okay. Remaining term as it is. M, C1 and C2 indicates these are the constant. This is going to get from figure 20.3 from the data book. Here is written where C1 and C2 are the constants from figure 20.3 from the data handbook. Clear? Yes, these all are the notifications. I'll directly take a problem. Only one problem is there. Many times has the same problem in the exam. Here, a Bellivellie spring is made up of 3 mm sheet steel with an outside diameter of 125 mm and an inside diameter of 50. Outside diameter of 125, inside diameter of 50. The spring is dished. I tell you what is the meaning of dished. Dished is 5 mm. The maximum stress is to be 500 megapascal. Determine shape load, deflection, second one deflection, stress at the outer edge, load for flattening the spring. As given, assume Poisson's ratio is 0.3 and D equal to 200 megapascal. If you have nothing as given, assume default Poisson's ratio is 0.3 only. Okay. Next. See here Bellivellie spring is made up of 3 mm sheet means T equal to 3, outside diameter means D naught, inside diameter means Di, dished means that is H. Maximum stress is 500. Sigma I am taking sigma I because in the question is asked stress at the outer edge, so I am taking sigma I. The Poisson's ratio is given. Next, from figure d naught by di values 100 d naught by di 125 by 50, this is 2.5. M equal to 0.75, C1 and C2 are constant. These are constant. You are going to get these all the terms from figure 20.35. Now write the first as asked deflection. Use the stress at the inner edge. Write the formula 20.20. Put all the datas. Okay, here only y is unknown. Y is unknown. Okay, you will get the equation in terms of quadratic equation. You will get solve that quadratic equation. Here you will get the quadratic equation here. Solve that quadratic equation y equal to this much. Okay, similarly shape load. Use the equation 20.19. Put all the data in this equation and find the value of f. Clear? Stress at the outer edge is asked. Write that equation as it is. Okay, then we get the answer 73.706. Clear? This is the question. Next, okay, this much only. Next is asked. Last one is asked for the load for the flat. Let's f equation 4EHQ 1 minus m d naught square. Then put once again all the data here. I get the answer. Clear? Here y equal to h. Clear? This formula I think you have to remember. I think we'll let us see once again. How to remember this formula? In 20.19 put h equal to 0. Sorry, y equal to h. In 20.19 equation put y equal to h. Then you will get this equation. In 20.19 equation put y equal to h. Then you will get this equation. Okay. Now this completes your Bellivellie spring and all the problems related to spring is over. Now I complete this module. In the next class I will deal with the brakes and clutches. Thank you.